rather than engage in an unseemly brawl with Polly about whether functions are functions from strings to strings or categories to categories, I thought that I would engage in an unseemly brawl with Jeff about his advocacy for model-theoretic syntax. And I've taken my title as a sort of facetious parallel to a book by Saunders MacLean, who wrote a book, a rather unreadable book, called Categories for the Working Syntactician, because category theory is one of the many ways that I'll talk about, in terms of which you can talk about what used to be called the Chomsky hierarchy, or the language hierarchy of theories of increasingly expressive power for talking about languages. So, in a series of papers, Jeff and his colleagues have proposed a distinction between theories of syntax that are, and these are the ones that we're mostly familiar with, generative enumerable, for which I'll use his abbreviation GES, generative enumerable syntax, and model-theoretic theories, MTS. The former category includes classical transformational grammar in all its versions, most proposals under the minimalist program, optimality theoretic syntax, tree-adjoining grammar, and categorical grammar of all kinds, including combinatory varieties of the kind that I advocate myself and that Polly has been talking about today. Only lexical functional grammar, head-driven phrase structure grammar, and at least the sign-based version of construction grammar are, with important reservations that Jeff spells out, admitted to the latter model-theoretic syntactic category. And it's striking, this sort of dangerous Ben sign comes with bullets that may rot your mind if you don't pay attention. All of the latter theories are constraint-based rather than rule-based, as transformational grammar originally was. Jeff and his colleagues define the model-theoretic syntaxes as those definable in terms of constraints expressible in weak monadic second-order logic. Like post-productions, recursion theory, or various automata like pushdown automata, and category theory of the kind popularized by Saunders MacLean, weakly monadic second-order logic defines a hierarchy of abstract families of languages, all of which are properly contained within the type 1 context-sensitive languages of the Chomsky hierarchy. You remember there were 4 levels: the type 4 languages, the finite state languages, the type 2 languages, the context-free languages, and then an enormous jump to the type 1 context-sensitive languages, which are actually not interestingly theoretically different from the type 0 Turing-complete languages at the top of the hierarchy. And all of these sort of are nested Russian doll sets of languages and accompanying formalisms. And that claim is consistent with claims by prominently Aravind Joshi and his students that human languages can be captured at the lowest level of this hierarchy, just one step above the context-free languages. And this is a very attractive hierarchy to be in. We can argue about exactly what level you want to live at, because all of these theories come with a guarantee of polynomial recognition and rules that are entirely monotonic. But Jeff makes a stronger claim, which is not compatible with these other views of this hierarchy, which is that only grammars expressed in terms of constraints can capture a further set of phenomena that characterize all languages of the world and all language users, which is robustness or resilience to gradient grammaticality, whereas where there are disfluences in utterances which make them technically, or in linguistic terms, ungrammatical, but are perfectly well understood by the users of the language. Neologism, as in Jabberwocky, but also as in every day one encounters new words with new meanings. And some other more abstruse deviations that I'll come to later. And this is a very painful observation to me, because of course this also excludes tree adjoining grammar and my beloved combinatory categorical grammar. So I had to think about this very hard. So I'm going to, model theory is familiar to most linguists from the analogy with first order predicate logic as providing a semantics that is isomorphic to the syntax of various artificial languages like programming languages and logics, and for that matter, arithmetic. And Lewis and Geach and Montague suggested very persuasively that the syntax of natural language was similarly transparent to its semantics, its very different semantics from those artificial languages. And this suggestion has been taken to various degrees of literality by linguists such as Barkhamparti, Keenan and False, Polly herself, Anna Salbocci, and for that matter, myself. This is not the sense of model theory that we're dealing with here. It's a quite different sense. Because Pullman follows Rogers, James Rogers, in taking the tree structures that a Chomskyan would view as associated with sentences a priori as part of the data, as models. A sentence is grammatical if its tree satisfies models, a grammar defined as an unordered set of formulae expressed in the language of weak monadic second-order logic. A second-order logic is, of course, one in which you can quantify over predicates as well as over individuals. It's monadic if the predicates are unary or properties. It's weak if the sets of individuals that those properties are defined over and the sets of properties themselves are finite. And unlike full second-order logic, which is rather unmanageable, weak monadic second-order logic supports useful model theories and that you can prove things with, and has many applications in programming language theory. And my colleague in the informatics department, Leonid Lipkin, has explored these very fully. It's interesting in the context of the first understanding of model-theoretic semantics that sentences like the following seem both syntactically and semantically to be monadically second order. So you can say Endicott has all the properties of a jerk, and you're quantifying over properties that jerks have, and thinking of a formula like the one in 1b. If that's the case, then the connection between model-theoretic semantics and model-theoretic, between model-theoretic syntax and model-theoretic semantics is rather direct. However, Pullman and Rogers, as I said before, are using monadic second-order logic as a meta-theory for the theory of natural languages in terms of their tree sets. And if you think of language in that way, you reproduce the neo-Chomskyan language hierarchy as shown in the slide. So if you take as your set of models the zero-dimensional trees, then your models are points, and the class of languages that you can deal with in your tree logic is the finite languages. If you have strings, they're one-dimensional trees, and you're dealing with the finite state languages. if you have what we usually used to call trees, in other words, two-dimensional trees, then you're dealing with the context-free languages, which include GPSG, as its name suggests, and some versions of GB and minimalism if you use if you choose constraints like relativized minimality and Manzini's restriction on the lexicon. But the hierarchy goes higher. If you take three-dimensional trees, then these are trees in which the branches can cross. And these are a very interesting set because it is proved after a long time after it was conjectured by Chomsky that natural languages include languages with cross dependencies. And if you go to higher dimensional trees, the only use that I've seen made of these the next level up is James Rogers' treatment of, I think it was clitic climbing, where he claimed that you needed three-dimensional trees to solve this problem. And I believe that that's actually really is a conjecture, but I think this may be the level of the hierarchy to which wrapping rules takes you. It may be level 3. And these actually correspond to what are called another way of thinking about the hierarchy is the multiple context-free grammars. The finite state languages are Chomsky's type 3, the context-free languages are Chomsky's type 2, and then the two multiple context-free grammars are the crossing level, the three multiple context-free grammars are the tree wrapping level, and so on up. It's actually an infinite hierarchy, all of which is properly contained in the context-sensitive languages. We don't need to go anywhere near context-sensitive, and that's a good thing because that is a very unconstrained level. All levels of this hierarchy have polynomial plausibility or recognition results, and all of their rule sets are monotonic. There are no rules that build structure, that alter structure that previous rules have produced in the style of transformations. The polynomial plausibility result, incidentally, is just a guarantee that there are nice algorithms for parsing these languages with, which are just generalizations of familiar things like CKY parsing and shift-reduce parsing. The actual polynomials are rather high, even for this level here, the CCG level. The polynomial value is n to the 6th in the length of the sentence, and any computer scientist will tell you that as soon as you're above n1, you're doomed, and at least n2. So that's the point of the polynomial thing. Now, Rogers showed that grammars expressed in this way, or like grammars expressed directly in the hierarchy using weak monadic second-order logic constraints to express them, were interesting because, first of all, they can be algorithmically converted to standard formalisms like GB and tag. And in the case of tag, this amounts to generating the entire set of elementary trees from the set of constraints. But Rogers pointed out that the constraint set can be orders of magnitude smaller than the grammar it maps onto, since many of the constraints are universal. And this is just, in theory, this is an efficient way of expressing the grammars that you're actually interested in. What this means is that you can express your grammar as a teeny-weeny set of constraints. You can get your grammar right by specifying those constraints, and then blow it up to something useful like the tree adjoining grammar tree set, and thereby maintain the very large grammars that you need if you're going to talk about natural language in terms of grammar at all, which of course many of my colleagues in computer science reject these days. But if you're going to do it, you're going to have a very large tree bank, and it's going to be very costly to manage, and maybe this is a way of thinking about managing it efficiently. Maybe. I think it's partly because of the beauty of this result that Jeff made it a definition in terms of weak monadic second-order logic constraints. Part of the definition of Model-Theoretic, I think I've this is the kind of thing that Jeff says we can take in our stride and mistype things on slides, of Model-Theoretic syntax. He gives the following, he gives some helpful examples of a convincingly universal, substantive universal, immediate dominance constraints on tree sets, where he gives a formula that says that every PP in the tree set that you're dealing with is such that there is something, Y, which is immediately dominated by the complement of the PP, of the preposition, that should be a P, in fact, and is the head of the construction. And he uses this simple example to point out that these constraints are not equivalent to language-specific generative and enumerative semantics, syntax productions or categories like the following. There's a familiar trivial rewrite rule here that says PPs in the language you're interested in have a preposition to the left of the noun phrase, and the categorical grammar category says the same thing, except that it singles out the word on the left of the definition as being the head of the construction, the PP, the result that comes to the left of the slash. Now, I think a linguist would expect that the choice of constraints versus rules would be entirely empirical. Transformational grammar started out by defining everything in terms of rules, productions, but it very rapidly became clear that if you wanted to do that using transformations, you were going to also have to include a lot of constraints. And Mark Lieberman once jokingly suggested in a class sometime in the 70s that maybe you could formulate the entire grammar in terms of constraints. And in fact, this was rather predictive, a prediction about the way the field moved for a while. But the argument from Rogers' tree automaton constraints is in fact hard to realize in practice. So I don't think that one can settle the question of whether it's better to use constraints or rules in terms of that generalization. Because in practice, as Rogers points out, the algorithmic advantage is very hard to realize in practice for two reasons. One is that there's an exponential blow up in the size of the objects that you have to deal with when you attempt to do that. And of course, it's not clear that linguists are in any position right now to tell us what the universal constraints are actually are. Pullen's empirical motivations for defining model-theoretic syntax as constraint-based therefore need to be considered independent from the Rogers generalization. So the motivations for defining it in that way are, as I said before, resilience to neologism, the fact that we daily encounter additional words that we have to add to our grammar, error in speakers or their slides, which we also write over as if they were no problem, and also children's ability to learn language from use. All of these come down in Jeff's account to the claim that generative and enumerative semantic theories, including tree adjoining grammar and CCG, assume that the lexicon is fixed. Now, it's standard when you're trying to prove properties of a grammar to close the grammar under a finite set of lexical items and to talk of it thereafter as generating all and only the strings of the language, an unbounded set, of course. And it's also standard to speak of language acquisition in terms of a finite sample of utterances from the language. However, it doesn't seem necessary to think of the child or adult who learns a new word, which the context and the rest of the grammar disambiguates, as actually having changed their grammar. Even in a minor sense, it just doesn't seem to be that is what they've done. And in this connection, it's interesting that all existing wide coverage grammar-based parsers that have been developed by myself and my colleagues in informatics include a wildcard for dealing with unseen words. You never run your parser, if it's a parser of any size and the corpus that you're dealing with, without encountering new words, novel, unseen words. And there's a wildcard in the grammars for unknown words, and this behaves rather like the star in a grep regular expression that you use in Unix for searching a file, where you want to, you need a pattern which says, I want a B followed by any string of characters up to a word boundary character. And the wildcard allows matching unknown words to be treated generatively as having any known preterminal category, where preterminals are things like part of speech, or in the case of categorical grammar, one of thousands of more specific categories that say this is something which wants such and such to its right and such to its left, and so on. You can be sure in using your parser that only a few, except in the limiting case of the child who's hearing their first sentence, which we'll come to in a minute, only a few of those categories will be compatible with everything else that you know about the sentence. And this means that you can parse the sentence even if you don't actually yet know what the word means. You can put it into your lexicon and find out what it means later. And of course, this is what the child often does. So this underlines the fact that ambiguity is not a problem of grammar. It's a terrible problem. Every computational linguist knows that actually that's the hard problem in parsing. You can parse with any grammar, you can parse with transformational grammar, but the problem is finding your way through the amazing ambiguity of natural language, a degree of ambiguity that we never allow in our programming languages, but is allowed in human language. So including wildcards in the grammar increases ambiguity, but so what? All natural languages tolerate an absolutely massive amount of ambiguity. In particular, I hope someone's timing me, by the way. In particular, ambiguity does not change the level of the grammar that you're at. You can have as much ambiguity as you like, and provided you stick to the class of rules or categories or indeed constraints that you've subjected yourself to, you don't move. Handling ambiguity in parsing is the central problem of NLP, which is solved by statistical modeling. Some people think that all you need is the statistical model in order to parse with some kind of direct transduction. I don't subscribe to that belief myself, but statistical modeling is absolutely crucial to practical parsing. In human beings, the disambiguation model actually involves access to all levels of representation, including semantics and pragmatics. And when I say pragmatics, I include common sense and understanding of the context. Statistical modeling also provides a basis for handling gradient grammaticality, since it allows any non-terminal to act as the start symbol. You're therefore in a position where you may only get fragments, categorized fragments of a sentence, but counting the number of disconnected constituents in something that looks like a sentence seems essentially equivalent to doing the same thing in constraint space, where you count the number of constraint violations as a measure of ungrammaticality. So, and finally, a category that I haven't actually, I seem to have left off the earlier slides, that Jeff identifies as needing to be addressed by linguistic theories, is quandaries, where you actually have a meaning for which there is, in the particular language you're speaking, there is no legal realization. And this comes out in sort of quasi-English, like his and my book, where there just isn't actually a way of forming that coordination in English. The parsing model is also fundamental to the process of language acquisition in the child, for whom all words are initially unknown. As Pullen points out in his articles, such a model is in fact central to the CCG-based model of child language acquisition that my colleagues and I published a few years ago. This is a model which learns it uses an algorithm called the EM algorithm, which is just the algorithm that you would think of yourself if you were faced with this problem. It learns a variational Bayes version of this thing for all possible lexical categories and all possible combinatory rule instantiations for which it's seen evidence in the data that it's presented with, which it's pairs of sentences and meaning representations, which it has access to from the context. So if the first utterance that it pays attention to is nice doggies, it's got a logical form meaning the dogs are nice, but it's got to decide whether nice means dogs or nice means doggies, nice means nice, and similarly for doggies. But it can, in practice, using real data from the child's corpus, which only actually represents about 5% of the data that the child is actually opposed to. This thing can learn, it learns a grammar that only exists in, if the linguist asks, well, where is the grammar? The fact is that the grammar is latent in the distributional model of all of these possibilities. But of course, most of the probability in mass accrues to those pairings of category and meaning that a linguist would regard as the grammar. There's still a residual possibility in the model that nice actually might mean doggy, but it's a very small possibility indeed, and maybe you can just reject it. And we show in the paper that I referred to that such distributional grammars generalize compositionally to unseen words. So after a certain amount of learning has taken place, if you present it with sentences from Gleitman's experiments with wag in the place of a transitive verb, then it knows that it's a transitive verb. It doesn't yet know what it means, but it knows what its type is. So here's my conclusion. I think that seen in this light, Jeff's call for model-theoretic syntax can be interpreted as a call for linguistic theories of all kinds to return to monotonicity in rules via a clearly identified near contract-free position, low on the weak monadic second-order logic, or if you like, multiple context-free grammar hierarchy. It's also a call for such theories to support type-transparent parsing models, robust to neologism quandaries like the my and his book, and gradient grammaticality induced by error. And that's also something that our learner is resilient to. It's also a call for type-transparent relation between syntactic categories and logical forms. And I've shown in passing that both are needed to support the theory of child language acquisition. So it's a call for a return to the position which was actually the position of the psychologists and computer scientists and linguists when I started doing this subject, which is that we all thought that we were actually working on the same subject and that our theories would inform each other. So thank you very much.